So good afternoon, everybody, and welcome to a new session of DaSSWeb, our webinar series on data science and statistics. And today we have the pleasure of welcoming Emilio Carrizosa. Hi, Emilio. Emilio Carrizosa is Professor of Statistics and Operations Research at University of Sevilla in Spain, and is also president of the MATH-IN, the Spanish Network for Mathematics and Industry. Emilio has served as president of SEO, this is the Spanish Society of Statistics, Operations Research and Data Science, and has been awarded the SEO medal in 2024, as well as the SEO FBBVA award for best paper in statistics and operations research applied to big data and data science. He has published over 150 papers in highly ranked international journals, primarily in operations research, but also statistics and data science, and applied fields as energy, chemical engineering, and hydrology. Emilio has since long developed an interest for the connection between optimization and statistics and machine learning. And today you will talk to us about generalized linear models in explainable machine learning, proposing a mathematical optimization perspective. Emilio, thank you very much for having accepted our invitation to join DaSSWeb. We are looking forward to your talk, and the floor is yours.
Thank you very much, Paula, for your very nice introduction. It's really great for me to be here sharing my thoughts or my perspective on a field that I am really excited with. I am an operations researcher, and I am coming from mathematical optimization and operations research. But as you have said, I have a strong interest for many years in the connection with data analysis, in particular with machine learning models, in which I have seen that we have many more connections for us optimizers because of the type of problems that are being addressed. But nevertheless, now when we have so many data and we are enjoying so powerful artificial intelligence or machine learning tools, which are black boxes and are very hard to interpret, perhaps, and this is something we have been, some collaborators and mine, we have been thinking for a while, perhaps it is time to go back and try to use as a bridge between these black boxes models and interpretability. Perhaps a nice bridge may be using more or less traditional data analysis, statistical data analysis tools. And in fact, what I am going to present today, and once I start speaking, it's very hard to stop me. So I have my watch here to try to control the time. But in fact, what I want to present to you is a couple of ideas in which the link is what I have said. So machine learning, explainability, machine learning is a challenge. And when we go to tools like linear models, or more generally generalized linear models, perhaps we have a nice bridge. So what I'm going to present is an overlap of a couple of papers that we have been doing. And when I say we, I mean myself with some colleagues and friends like Renato De Leone and Marica Magagnini, Università di Camerino in Italy, Thomas Halskov and Dolores Romero Morales in the Copenhagen Business School, Antonio Nava in the University of Seville, and Jasone Ramirez Ayerbe now in the University of Montreal in Canada. What I want to start is if we go back to science, to biology, and we take some sentences from Lamarck. Lamarck was wrong with his idea, which was not really evolution, but he talked about the power of life, which tends to build organizations. So things are in life are more and more complex. This is not really true. I mean, evolution and Darwin's principle are the say more fitting better to reality than this, but we have seen this in art, for example, and not only in art, we have seen also in data analysis. In data analysis, if we go to the simple, I would say what is simple and is roughly the linear model. And when we have a set of covariates, we are talking about the tabular case, of course, we have a set of covariates and we want to have a prediction, and we are trying to make this prediction just by summing things. So a sum of coefficients to be determined. And with these coefficients, we are going to have a nice interpretation, and at the same time, under some assumptions, these are going to be very accurate prediction models. And interpretability was I would say, in the very beginning also of linear models. And if you go to the times of Galton with linear regression, in fact, it is not only the interpretation of the coefficients, but even the fact that you could build a machine to make such a prediction, a physical machine in which you could interpret the coefficients physically. You could touch somehow the coefficients. So this was the origins, I would say. And as an extension to this, we can consider generalized linear models, in which, of course, the Gauss linear model is a first case in which we are just saying that we have that response variable conditioned to the covariates has an expectation, which is a linear function of the covariates. But as soon as we introduce some linking function, G, and for simplicity, we are assuming that it is strictly increasing, then we may more or less have different type of models in which you have nonlinear relations, but at the same time retaining the idea of interpretability, the beta coefficients there with some interpretation. So you obtain, for example, the logistic regression model in which, of course, we are having that it is now the logarithm of the ratio between the probability of success and failure, which is a linear function of the covariates. And we have the interpretation of the betas, a little bit more complex than in the linear model, but still we have an interpretation of the betas. Same if we are thinking of a model in which the response is taken non-negative integer values, and we have, for example, we assuming that the covariate, that the response variable is a Poisson variable, so that the logarithm of expectation is a linear model, because the rate of this Poisson is an exponential of a linear model. And again, we are having this interpretation, some interpretation for the betas. So this has been, I would say, the 20th century. And in the end of 20th century, an alternative, I would say, procedure, which is also very accurate and also quite interpretable, is started. Is the idea of classification and regression trees, and more generally, the idea of random forests, if you want. It is definitely easy to explain to a non-expert. It is all coefficients intervening in the model can be easily explained and interpreted. The drawback, of course, is the lack of continuity when you're in the border. So if you're around the border of any of the regions, then you're having a big jump at discontinuity, which may be quite uncomfortable. But nevertheless, we can see that these models are clearly transparent and interpretable. And this was what we have seen in data analysis in general till, I would say, the end of the 20th century. But if we go to the very end of 20th century and our century, 21st century, we are, I would say, in the interpretability blackout, in the information blackout, because we are having black boxes all the time. And these black boxes, the guilty, I would say, is the idea of neural networks. So now with neural networks, we may say that we have very accurate prediction processes, not only for tabular data, but also for time-dependent or space-dependent data, and many more complex structures. But of course, we have lost the easiness of interpretation that we had in the past with models such as the linear models or the generalized linear models, or these tree-like variants. Nowadays, in order to make a trade-off between interpretability and accuracy, we could have something like, okay, not everything is black. We have a little bit of gray, because many people are working or trying to obtain explainability from the data at the same time that we have a strong accuracy, sharp accuracy, and many people are working now in this in this domain, especially because even high-stake decisions need to have some sort of interpretability and even some regulations, for example, in the European Union about that. Different approaches have been considered in the last years. For example, just using simple models, counterfactual explanations, so some sort of post-hoc analysis, and also trying to say, okay, I have my model, which may be, I would say, in the black, but let's try to make a post-hoc approximation, which may be much easier. So I have marked in blue 3 different keywords, which are simple models, counterfactual explanations, and LIME. And I'm going to talk about the 3 of them, or I will try to at least to talk about the 3 of them, connecting, showing in particular that when we reduce to a particular class of simple models, and I'm talking about generalized linear models, things can be, the output can be easily explained. And also, as you will see, post-hoc models like LIME, so local interpretation, local approximations can be easily obtained. And also, if we are talking about post-hoc decisions such as counterfactual explanations, they are easily constructed. In any of the things I'm going to discuss right now, this, I would say, secret weapon is optimization, because I know this is a bias of me and my colleagues coming from operations research, but we see all these challenges, in fact, these previous challenges, as mathematical optimization challenges in which if we are interested in having explainability, then we should look for some sort of sparsity or something like that, or perhaps reducing the class of prediction models to a specific class which is more or less interpretable or explainable. And at the same time, of course, accuracy is a must, and optimizing the accuracy is in the end an optimization problem. So, in fact, I would say that to me, the key to address these problems, or at least a powerful tool, is mathematical optimization, because anything can be expressed as an optimization of one criterion or several criteria. And in this case, we are talking about multiple objective optimization problems, as you will immediately see. And at the same time, if you're having desirable properties for your model, it is just a question of adding constraints to the problem. I'm not claiming at all, of course, that these problems are going to be easy to be solved. Definitely not. Some may be easy, some may be not that scalable, which is also a must in modern data analysis times. But at least we may have a conceptual framework in which everything is reduced to optimizing one or several criteria, and there are a set of constraints defining the rules of the game, I would say. So, very short commercial. Now we are in an online seminar series, but I want to talk about another online seminar series, which is the Euro online seminar series on operations research and machine learning, which is supported by Euro, the Federation of our societies in Europe. We started, in fact, yesterday, and we are looking forward to seeing you all next Monday at 4:30 Spanish time. So when 3:30 Portuguese time. And here you have the QR in case you want to subscribe to our mailing list that we promise we are not going to use for any purpose excepting sending the information about our fantastic speakers. Now, the talk. And the first of the 3 problems, or the 3 topics I want to touch, is LIME. So what is called the acronym of Local Interpretable Model Agnostic Explanation, the idea. And the idea is, of course, very natural for all of us in data analysis. And it goes back perhaps to the idea, or to the statement of Leo Brayman with his idea of the 2 cultures putting together machine learning and statistics, traditional data analysis. And the thing is that, okay, the world may be too complex to be modeled by a linear relation. in many circumstances. But perhaps if I am interested in not the full model, but in a model around a point. So, for example, I have this point in a cloud, and I am only interested in knowing the behavior around this big blue point. Perhaps if I do like this, if I consider only the neighborhood of the point I am considering, and I discard the remaining information, I may be quite satisfied with a linear model, whereas if I am considering the overall cloud of data, so considering also data which are far away from the point I'm interested in, or most interested in, for points far away, the model may be very bad, but for points which are around the point, a linear model may be good. So the idea may be that, okay, we are now talking about deep neural networks and so on, but perhaps when I'm looking at a given record and I'm trying to explain why a given prediction is given, I should not consider the full data set, but perhaps those data which are in the neighborhood of the record I am considering, and perhaps around the data, around this record, a linear model is Gauss style, is easy to interpret, easy to build also, and also quite accurate. So this is the idea of LIME. In fact, it was introduced a few years ago, and the idea is simply that, yeah, I may have a very complex model, but if I am going to a practitioner who needs to make a decision according to this very complex prediction model, perhaps he or she is not that satisfied, and he or she would be would feel much more comfortable if instead of having a black box such as I don't know, a deep neural network, something like a tree or a linear model or a GLM could be provided. So the idea is to make a replacement of saying, okay, around the point I am considering, let's take a linear or a generalized linear model and forget about the remainder of the cloud of points which may have a different behavior. So the idea is that I may have a black box model, for example, a deep neural network, which I assume it is available, and I can make predictions for any record I am interested in, any point I'm interested in. I have a specific record X, and the idea is to do some sort of linear surrogate model around the points, as you have seen in the picture before. So the idea is that I am expecting, if I do this linear model around the point, is that I am expecting that points in the neighborhood of this record are going to behave more or less, predictions are going to behave more or less like in the linear model. I am not discovering anything, because what I am doing basically is doing a Taylor expansion of order one. So I'm linearizing the perhaps very complex model by a linear model. The same thing, of course, well, this is what you can see in the original paper by Ribeiro and co-authors. But of course, the idea is naturally extended, and it has also been extended. If instead of looking for a linear model, you are looking for a GLM, just by introducing a link function there, the same trick, the same idea. The point is, what happens if I want to make LIME collective? I mean, I am not interested in making a prediction around the point, so I'm not that interested in obtaining a linear model around a given record, but I have a set of records. Okay, if I have a set of records, you may say, yeah, it is a question of making the analysis separately, in parallel perhaps, for the different records, and that's it. I mean, here you have 3 blue points, and I'm building 3 linear models around these 3 blue points, and that's it. The problem is that, of course, if these 3 red linear models are not properly connected, then I may obtain strange results, in the sense that perhaps just a slight change in one of the reference points, in one of the blue points, yields a completely different explanation, and a completely different explanation may be very difficult to explain. So this has already been noticed, and what I would like to do is to do this, but making some connection between the different models. So what we have addressed in a recent paper by Thomas Halskov, Dolores Romero, and myself is to build in one shot a surrogate GLM around each potential record. But in fact, what I'm looking for is for each of the potential records X, I'm building a linear model or GLM around the point. And the thing is that instead of determining the vector of betas, now I am interested in determining the function beta that for each X gives to me the vector beta of X in the generalized linear model. So the problem when I had the beta is that, in fact, I may determine or I may estimate the beta according to, I don't know, maximum likelihood principles, for example. But now what I have is a functional, and it is a functional that I am interested in addressing. So in order to determine this optimal functional beta, what we may do is first to define some loss function of to compare the black box prediction and the one given by our GLM, some weight, because we are talking about points around, but we should measure in a precise way what we mean by being around, or how close a point X tilde is around our point X. Of course, for the loss, we may take the log likelihood, for example. We are going to take the expected weighted loss with the P. So the expectation is with respect to a probability measure, which may be, for example, the discrete uniform if we are considering only the data points, but we may have something different, like, I don't know, RBF functions or something like that. For the weighting function, it can take some sort of kernel of distance, and this is for a given X. So when I have to choose between one beta, a functional beta, and another functional beta, how do I compare? I may take the beta minimizing the expected delta, so the expected error with respect to a different Q probability measure, which controls the relevance I give to the different X records in which I want to make this approximation. Okay, but I also need to determine my functions beta should be in a given class of functions. What class of functions I am going to consider? Let's make it easy. Most of the time, or first in my next slide, I'm going to consider the unconstrained case in which I am allowing the beta to be any function, any functional. So in any case, the optimization problem, and this is why I was saying that in the end, to me, anything is just an exercise of writing an optimization problem that later I need to show how to solve. But for me, the problem is to determine the functional beta in a given set of feasible functionals that minimizes a given error, where the error is the expectation of the delta, and the delta is the expected weighted loss with respect to a loss function, a weight function, and expectations are given with respect to two probability measures P and Q. Let's go to the simple case in which I have no constraints. So I am allowing full freedom for the selection of the beta. And let's go to the simplest GLM, so the linear regression model, assuming that we are having a loss, the quadratic loss, and so on. If we were in the linear case, in a traditional linear case with a finite data set of points, in fact, where in order to obtain the optimal beta, what we need to do is under the assumption that we have full rank in the design matrix, we take the inverse, and we have with the normal equations we have a closed formula for that. Well, and roughly the same assumptions, but in this more general context, then we can derive the optimal functional, which is going to be related by this. I mean, this is just the extension of what you would have in case you're having a traditional linear model. So that's it. So in case we are having no constraints on the linear regression model, we have even a closed formula. I'm not claiming that this closed formula is going to be easy to evaluate, because we have here the expectations, we have here the inverse of the matrix and so on. But in any case, we have this. And also the interesting thing is that, okay, the beta star, so the optimal functional may have very nice properties in the sense that, and these properties, and when I'm talking about nice properties, I'm talking about smoothness, for example, continuity or differentiability, and these are inherited simply by the selection, by the choice of the weighting function omega. So if I am assuming that the weighting function is continuous and bounded, then I may obtain that the beta star is a continuous function. Same thing if I am having differentiability in the omega function, Lipschitz continuity, etc. And also, this that happens in the linear case is extended under some technical assumptions, and I am skipping all the details. And for those who are interested, you are welcome to have a look at the paper, which is, you will see later the reference, but it is in ResearchGate, already available. But the thing is that the assumptions are the traditional ones when you are talking about GLMs and you're looking for the maximum likelihood estimate. For example, uniqueness of maximum likelihood estimate and things like that. But under the same, roughly under the same condition of continuity of the weighting function omega, we're going to have continuity of the beta star. The problem is that the beta star is not going to have an easy or at least a closed formula, but it is going to be obtained by taking gradient equal to 0 and trying to solve locally with the implicit theorem function the beta star, as usually in maximum likelihood for GLMs. The nice thing with this is that you can obtain, for example, this is one standard data set, the Boston-Hausen data set for regression. And here we have all the variables, and we are seeing in these pictures for the different covariates that each covariate has its own beta, of course, and how these betas change when we change the record X in which we are doing everything. Okay, the thing, of course, is that the Boston-Hausen dataset is not 2D, so we have made PCA to go to a two-dimensional case, and then we have plotted these coefficients beta, seeing, for example, that in some features, when you vary the record, you obtain a very slight variation in the coefficient, whereas in some others, you can change even from having a positive dependence to a very negative dependence here, just by moving. So the coefficient beta can even change the sign when we are taking one record instead of another one, which is not surprising because we are talking about a local approximation around each of the points. Okay. Finally, final word on these GLMs. As I was saying, I wanted to first have some link between the different models, and the link, as you have seen, is just taking a sufficiently smooth weighting function to model the proximity between different points when you were taking the function omega, so weighting function. But if we are interested also in explainability, we may also be interested in having sparsity, so identifying which are the covariates which are most relevant. Of course, if we are considering one single record, we may say, yeah, let's do some sparse regression, take lasso regression or some elastic regression, for example, and in this case, you can control the features which are relevant and so on. But of course, the set of features which are relevant for one record may be different from another record. This may be nice, and I don't object about that. But perhaps if we take for a moment the stakeholders' perspective, we may be interested that, okay, I would like to know which are the features which are overall of importance for my population of records. Then perhaps out of these features, I may select different ones, different subsets, doing, as I said, some lasso or elastic net or something like that approach, different for different records. But I would like to have some global detection of features which are globally relevant. So instead of considering as a class of functionals beta the class of all functionals, we may consider, and this is what we are going to do right now, the class of functions which are zero, which are exactly the zero function, excepting in at most k components. So in the end, if we are considering this, what we are saying is select globally the k, or at most the k most relevant features, and then use locally the approach we have been describing, leading to plots like this. Okay, how to do this? Because this is what we want to do, to make some sort of global coordination. This would be the stakeholder seeing from the above all the models and trying to have, for example, in this case, the same features selected for all the individuals. Perhaps, as I said before, making a sub-selection later in a second stage using some sort of lasso for the different records. Okay, if I want to use this, if I want to make this, the idea is to use again the same formulation. And this was, as I said, the strategy of an operations researcher, which is okay, which is the constraint you're interested in. You want to have at most k features involved. Add the constraint that you have at most k features involved. But the problem is that once we have written this, we need to solve this optimization problem. And this optimization problem is not easy at all, but nevertheless, we can say, okay, let's use binary variables indicating whether I'm using or not each of the different features I had in my problem. I have the constraint that each feature multiplied by this function should be equal to 0 for all the points. This is not that nice, but in any case, I have rewritten the problem in a different format, which is much more tractable, which is, okay, let's define pi of z, the function that for each z gives me the optimal value of the inner problem. So the problem I am interested in solving is a knapsack problem with very simple coefficients for the moment. And of course, it's the difficulty is that the pi function is highly nonlinear, for sure, non-convex. But the thing is that, yeah, we can do something not that original, which is, okay, what happens if this function pi was linear? If this function pi is linear, then in this case we have a standard knapsack problem, but with all coefficients equal to 1. So the optimal solution of this problem is straightforward, because the only thing we need to do is to sort the coefficients in the linear objective. But pi is not linear, but I can do sequential linearization, so I can successively linearize. I linearize, I solve the problem, and this is straightforward to solve this problem. And I repeat the linearization. Of course, the gradient does not need to be the gradient. I can take finite differences because I have only the 0, 1 variables, and that's it. I have put here coefficient equal to 1 because I have been talking about the zero norm, so that I'm just counting the number of features I am interested in. If instead of this I had a different cost, a different measurement cost associated with each of the features, then what I would have here is the same type of constraint, but with different coefficients. And in this case, this problem would not be anymore so straightforward. This could not be solved in linear time. It could be, it should be then a standard knapsack problem. But nevertheless, we have very good heuristics and very good solvers to solve the problem to optimality for sizes which are not that big. So some nice illustrations, for example, going again to the Boston housing regression data set, we can consider that for the different number of features, how the global error is decreasing. Of course, the higher the number of features, the lower the error. But we have here the Pareto front for this bi-objective optimization problem of minimizing the error and minimizing the number of features that I am using. And if I am making the parametric analysis on saying, what happens if I take one feature? What happens if I take two? If I take three, etc., we obtain something like that. For example, LSTAT is the first feature to be introduced. If we have two, these are the two ones. As I said before, I may introduce some coefficients here. And if I introduce some coefficients here, I may say, for example, let's make LSTAT very costly. And if I do like this, so introducing non-equal costs, in this case, it is not anymore the most the most interesting one, because now it is very costly. So I have a completely different or somewhat different scheme. What I have shown for the linear regression case can be done for logistic regression, Poisson regression, and many others. Very quick. Two, again, in linear regression, in generalized linear models, another idea, which is, again, we had, as we have seen before, we can do Lime and we can do collective Lime, as I have shown to you very easily. Well, at least not that difficult in the GLM case. But the thing is that, okay, this is the solution I would have obtained if I do a linear approximation, but going to say Mark's principles, we may say something like, this is my prediction model. If you don't like it, I have others. And the idea is to say, okay, this was my GLM, but perhaps I have other alternatives which are not that different in terms of accuracy around the point, and some may be more convenient than others because some may be, for example, sparser than others, or may have more coherent with some user expert knowledge. So one possible idea, and this is again the traditional approach of going to multiple objective optimization, would be to make some balance between accuracy and some sort of sparsity. We can also introduce some sort of fairness, etc. And in the end, what you're obtaining is different points. The points are the different models, which are having a different trade-off between accuracy and other criteria such as sparsity. But now I want to mention something which is much less common, which is, no, I'm not looking for a trade-off between accuracy and something else. What I'm looking is, instead of looking for one model, I'm looking for a menu of models. For example, in this case, 5 different models, which are all good. So the 5 different models are good. Not optimal, because the optimal might be perhaps the GLM solution, but they all are good, and at the same time they are different enough because they are they provide different options for explaining to someone these models. And they may be different in terms of, for example, the features that they have been using, or the coefficients that they have been using, or the predictions at a given reference point, or if we are talking about counterfactual analysis, and I will talk about that very quickly in a moment, that the counterfactual solutions obtained are very different. So this is, of course, not new. And again, if we go to the statistical modeling and the two cultures, the paper by Leo Brayman, this is what he called the Rashomon effect. So that the idea that different models may have a similar accuracy, but may have some different properties with respect to a secondary criterion, which may be this idea of diversity or dispersion. And this, if you go to the OR, the operations research literature, these dispersion models have been addressed by many people. If we go to our GLM context, we may consider that we have a GLM, we have a random sample. We are looking for a number of models, and we are interested in solving, or at least addressing, a given by objective optimization problem, in which we want to determine a set of P different generalized linear models, which are simultaneously good, so that they obtain some sort of trade-off between accuracy with respect to a given measure and dispersion with respect to a given measure. And and for this set of P functions that we are looking for P functions satisfying some constraints on, say, accuracy, because we want that the P models are good enough, and also sparsity to have some explainability. Okay, so in order to model accuracy of each of the models, of course, we can do the traditional things. When we have not one model, but a set of P models, we may consider the accuracy of the set as the minimum accuracy, the average accuracy, something like that. For the dispersion, I'm not going to consider many. I'm not going to the details, but the idea is that, of course, we may consider some sort of norm if we are considering the dispersion or the disparity between two different models with coefficients beta and beta prime. we may be interested in measuring this by the norm of the difference between the two, the difference in the prediction, or, for example, the coefficients which are non-zero, which are not vanishing in the two models. This, if we have two models, if we have P models, of course, we can consider as disparity of the set the minimum dispersion, the average dispersion, etc. With this is the constraints we may consider, the accuracy that we want to have a set of P models which are all accurate enough, because the accuracy defined as before is above a given value, and for example, that they are sparse enough, that none of them uses more than a given number of non-zero coefficients. We are trying to generate the Pareto frontier. I'm skipping that, but these are the traditional ways of scalarizing the problem, just, for example, by taking a convex combination of the two criteria, more in some sort of lasso approach, I would say. Making a straightforward exercise for, I would say, master students with some background in operations research. This is more or less straightforwardly written using these nasty big M constraints. We cause a lot of numerical troubles, and there are many more efficient ways to address this, but this is, I would say, the cleaner formulation we could obtain. For the different types I have been mentioning before, we had something like that. The thing is that in any case, the problems we are addressing are not nice, in the sense that these multiple objective optimization problems are usually non-convex, on top of the fact that may have non-linear, non-continuous variables, because they may have integer variables, and they may be some sort of nightmare. But in any case, we can use many simple. It may be easy to obtain feasible solutions. So once we have obtained one feasible solution, a feasible set of P prediction models, it is a question of, I don't know, doing some heuristic like variable neighborhood search, for example, is something that we have tried to come up with some solution, which we are not sure that we have obtained the optimal one, but at least we have some results. Same if instead of having the P dispersion, we have the conditional P dispersion, which means that we already have one or several models. For example, I have solved my problem with the ordinary least squares model, and I say, yeah, but I want to have three models which are perhaps not that good in terms of sum of squares, but almost as good, or at least they are good, and at the same time that they are very different to the OLS. What can we do? Well, this in OR has been named the conditional P dispersion model. The thing is not that now we need to consider the accuracy, the dispersion between the different criterion, and the dispersion between the different new criteria and the old criteria, I would say. This is the same. I am skipping this. We have the paper almost ready. The thing is that, yeah, you may have something like this, for example. We have said, we're looking for three different models, having, for example, 5 non-zero coefficients. And here you see, again, in the Boston housing logistic model, in this case, we have that if we have 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. These are the 5 coefficients which are non-zero, and of course they are different. They are not identical in the different models. We see that in this variable in this covariate, more or less, they have an agreement. But in some others, you see that there's a displacement between one variable and another. So what we are offering is if you want to have only 5 non-zero coefficients, these are the coefficients of the 3 linear models, which are complementary to the 3 lasso models obtained, and things like that for different coefficients. So this is the type of output we obtained with this procedure. And I want to devote not more than 4 minutes to counterfactual explanations. The idea of counterfactual explanations is that, okay, I have already a classifier, so I'm not going to make a prediction anymore. The prediction is already given, and perhaps it is given by a black box. Now I have the prediction, and I obtain, for example, that I am classified in the negative class, and I am asking for an explanation for that. Why have I been classified in the negative class? And I am expecting to have something like that. okay, these are my your features, but if your features instead of these were these ones, then you would have been classified in the positive class. So roughly speaking, the problem I am interested is somehow saying, okay, I have a record and I want to determine the minimal perturbation of my record in such a way that I am classified in the opposite class. This is what I would have in a classification problem, but I may have in regression. And the thing is that in the end, what I'm trying again is to balance the distance, because I want to have a small perturbation, and at the same time, I want to have a big increase, a big jump in the prediction. Okay, so this is the idea. Many people have been working on that from an optimization perspective, depending on roughly on the type of classifier or the prediction model you're having here. You're going to have different mathematical optimization tools to address these problems. Also, the multiple objective part in which you want to indeed address simultaneously the distance. So the amount of perturbation you're introducing, and at the same time the jump you're doing in the prediction. When we are going to the GLMs, what we are having is again a GLM. Let's assume that the positive class is something good. It's not a disease. It is something we are looking for, and we are looking, once we have a record, which is our focus. We are looking for the changes with minimum cost that cause my prediction to increase from this value as much as possible. So again, we may write this as a bi-objective optimization problem of determining the solution, which is actionable, so that is meaningful, that we can believe that this perturbation is doable. In such a case that we minimize the cost and we maximize the prediction. Writing one of the constraints, we are reduced to solving the problem, as I said before, of determining the x at with minimum perturbation, so that the prediction is above a given level. And the nice thing of the generalized linear models is that since we have only the link function here, in the end we write that as a linear model. Depending, of course, on the structure of the problem of the actionable set, we are going to have a different type of optimization problem. Depending on the way we measure the cost, because we need to have some sort of dissimilarity, but we may have also some sort of complexity, because I want to penalize density, because I want to have a sparse solution, indicating that I have only a few features to change to attain my aim of having my prediction above a given value. For the dissimilarity, I'm going to use some sort of distance. In fact, generalized distance, because I am not assuming a symmetry in the distance, and I am going to compose it with a convex increasing function to have, for example, the squared distance, Euclidean distance in the game. Just one word of caution, and it is that people are traditionally using here distances, norms, so symmetric functions, and it is not, in my opinion, a good idea in problems in which, for example, increasing is not as costly as decreasing. Finding a job with a better salary is much more difficult than finding a job with a worse salary than the one I have, for example. But again, if you go to the literature in operations research, you will see many opportunities of models for that which are tractable. So having something like this, we want to minimize the perturbation. We want to this is the cost, and this is and we want the prediction. And the nice thing, as I said before, is that since we are in a GLM, we have a linear model, a linear constraint, that the prediction is high enough. So for this type of problems, you can see here a couple of papers, but I want to go in my last 2 minutes, I would say a little bit beyond this, considering, for example, collective C counterfactual explanations. Again, because I want to play the role of a stakeholder, that I want to give an answer not to one individual, but to several individuals with all the loans refused, and I need to give an explanation to them Of course, I can do what we call the one-for-one model, so I give an explanation for each of the individuals, and I can do this separately. But of course, I can have some linking constraints. For example, that I want to have a global sparsity in the sense that I want to control the overall number of features that I am using. So this leads to formulations that may be nice or not, but again, that at least for not too large data sets and using, say, Euclidean distances or variants of Euclidean distances, we can address these problems using standard solvers for quadratic optimization with linear constraints, for example. Yeah, again, another word of caution is that, of course, if we do something like that in counterfactual analysis, here you have what happens with 10 different instances. These are the changes obtained. And we have done this with logistic regression, and we have done this also with random forests. And the features we are saying we are moving are not completely different, but they may be different, which means, of course, that we are not indicating the features that make different the life of the individuals, but we are simply changing the features in such a way that the classifier would give to us a different answer. And if we are using different classifiers, such as, for example, logistic and random forest, of course, the treatment may be different. Same thing if we have, one nice thing is if we have, we are looking for one counterfactual for a full population. So because we want to have a prototype, this optimization problem is not that difficult because the only decision variables are those affecting the counterfactual. But this is nice because we may consider now the case in which we have the full population, and we may say, okay, yeah, I want to have three populations, three counterfactuals for the overall population. And this would imply that we are going to define these three counterfactuals, and we are going to cluster the individuals, not in terms of their coordinates, but in terms of the model or the prototype they are going to follow. How to address this? Okay, these many models, so that we need to determine these points and to determine the clustering. We may do many things, but in fact, what we have done is simply sort of k-means approach for this. And this way you obtain, for example, for the Boston housing dataset with logistic regression, we have these are the coordinates of the three prototypes, and these are the clusters, so the coordinates of the clusters in a heat map associated with the first, second, and third counterfactual. And I promise this is the very end. In what I have mentioned on counterfactuals, I am assuming that my black box, my deep learning model or whatever, or my GLM if you want, is already fixed, and I'm not going to feed it anymore with data. What happens if I have some sort of uncertainty in my classifier, in my GLM, for example, and I'm looking for counterfactual solutions which are robust in the sense that they are not sensitive to a small change in the model building the counterfactual. So the idea, suppose we have, like before, I want to minimize the cost, I want to maximize in my GLM the prediction, I have the sample, these are the betas I obtained for the sample, but now I change the model because I am feeding the data set with a couple of more data. Of course, I may say, yeah, I'm going to have a continuous distribution. But if I'm having, as I had in many of these data sets, some, for example, binary variables, I should not allow that I have a continuous model. And the thing is that I should perhaps, one robust strategy or a conservative strategy would be to say, okay, I am allowing that I'm changing the distribution of the data, but the support is going to be the same. So I'm not inventing any data. Any record I am creating it has been observed before. And the only thing I'm changing is the frequency of the different records. So changing the frequency, of course, I would change, and then I ran the GLM. Of course, I would obtain different results, and I would be interested in doing. Okay, let's do the solution X, which is of minimal cost, but at the same time which is with highest prediction in the worst case analysis. And in the worst case is when I have my beta in a given set. And my beta in a given set does not mean that my beta is in a ball, which is the traditional thing. Because if I am assuming that I have a GLM and I am doing a maximum likelihood estimate, my beta should be in the set of maximum likelihood estimates when my data set is having the same support than the one I had, but with different frequencies. And for the frequencies we have used to measure this just using some divergence, in fact, the KL divergence. So we consider this optimization problem. The inner problem is a more or less simple one. This is not a simple one. Once we have obtained the optimal beta, then we have a concave optimization problem. So the idea would be to use some sort of cutting plane strategy and reduce the search, our efforts to solving the inner problem. So what we are going to do is to say, okay, let's assume that our feasible betas are those which are maximum likelihood estimates when we are changing the distribution of our data sets, but we are changing this under control in the sense that the divergence, the KL divergence between the original distribution and the new one is below a given value. We need to make some assumptions, which are, by the way, the traditional ones to have existence of maximum likelihood estimate, uniqueness, etc. And well, these problems are not simply solved because this constraint amounts to write this constraint, assuming this uniqueness, etc. But if we do this, then we have a nonlinear non-convex constraint. Then we have results like this. This is the error when I have no robustness. This is the error when I have the robustness when I'm allowing going beyond and beyond and beyond in different models with logistic regression, Poisson regression, OLS, etc. And just to finish, the takeaway messages I wanted to have from this presentation is that machine learning methods may be black boxes, but traditional statistical data analysis tools, and in particular GLMs, may be very helpful. Of course, you are having multiple objective optimization as a key paradigm, and the optimization problems are definitely hard. But at least if we are happy with using heuristics, then these problems can be addressed. I don't say closed, solved to optimality, but at least addressed. And this is a field in which you have many, many opportunities coming from statistics, coming from machine learning, coming from optimization. Here you have my email address. This is a QR with ResearchGate, where you can find all the papers from which this stuff is taken, and also my LinkedIn profile in case you're interested in sharing some information with me. And that's it. Thank you very much.